The ground moves before the machine arrives. Not a tremor, not a warning, a slow, rhythmic compression of earth, felt first in the soles of worn leather boots, then in the knees, then deep in the chest cavity, where it settles like a second heartbeat that does not belong to you. It is 1872, a Pennsylvania hillside. Dawn has not yet separated itself from night, and 43 men stand in the gray margin between darkness and labor, holding tools that feel suddenly inadequate. Their breath rises in identical columns of white vapor. They do not speak. There is nothing to say. They have heard the stories from the men who worked the Ohio line, and the men before them who broke ground at Cumberland, and before that, the ones who never came home from the Allegheny cuts. Then it appears. It comes around the bend of a temporary track laid the previous evening by men who worked through the night without lanterns, guided by touch and instruction, and the particular desperation of a deadline that answers to no man's suffering. The machine weighs 312 tons. Its boiler alone stands 11 feet tall. Its driving wheels, 4 of them, each one taller than the men watching, turn at a cadence that sounds less like machinery and more like a massive animal breathing in a rhythm of absolute indifference. The foreman does not call out. He simply steps aside, and the men on either side of the cut step aside with him. Because there is an unspoken understanding that runs through every rail camp from Georgia to the territories. The machine does not stop. It was not built to stop. It was built to move forwards, through shale, through granite, through mud, through whatever organic or geological matter happens to occupy the space designated by men in offices 300 miles away as the right-of-way of progress, including on certain mornings men. Between 1865 and 1890, American railway construction consumed more than 30,000 lives. Engineers called it acceptable loss. Shareholders called it overhead. The men who died mostly called nothing at all, because they were buried in unmarked ground beside the very lines their bodies helped lay, their names recorded in ledgers that would later be lost to fire, flood, or simple indifference. This is not a story about the railroad. It is a story about the machine that built it, and the civilization that looked away. There is a particular kind of monument that a nation builds not in marble or bronze, but in motion. Not the statue that stands still in a city square gathering pigeons and the slow erosion of weather. Not the arch, or the column, or the carefully inscribed wall of names. The monument that defines the American 19th century is kinetic. It moves, it consumes, it does not pause for ceremony or grief or the inconvenient weight of moral accounting. It simply advances, mile by mile, county by county, state by state, dragging civilization behind it like a chain. The locomotive and the machines that built its roads became the central icons of a nation that had decided, at some fundamental constitutional level, that speed was virtue and expansion was destiny, and that the distance between the Atlantic seaboard and the Pacific coast was not a geographical fact to be accepted, but an obstacle to be demolished. And demolished it was. Between 1860 and 1900, the United States laid more than 160,000 miles of railroad track. To put that figure in physical terms, if you took every rail spiked into every tie during those 40 years and laid them end to end, you could circle the earth more than 6 times. The ballast alone, the crushed stone packed beneath each section of track to distribute the weight of passing trains, required the excavation and movement of more earth than any human project since the construction of the Egyptian pyramids. This did not happen with shovels. It happened with machines, enormous, coal-fed, steam-driven machines of a scale and violence that the previous century could not have imagined, and that the current one has largely forgotten. Chief among them, the steam excavator, the rail-laying engine, and most consequential of all, the heavy grading locomotive, the class of machine that would come to be known, in the camps and cuts along the advancing frontier of iron, simply as the beast. Here is the paradox at the center of this story. The machine was a miracle. There is no honest way to frame it otherwise. It compressed decades of human labor into weeks. It moved mountains, literally, geologically, measurably. It made possible a nation that could speak to itself across 3,000 miles of continent. that could move food and people and commerce at a speed that rewired the entire economic nervous system of a civilization. And it killed the men who operated it with a consistency so reliable, so predictable, so thoroughly documented in the internal records of the railway companies themselves, that it could not be called accident. It could only be called policy. That is the question this story asks. Not whether the machine was powerful, it was. Not whether the railroad transformed America. It did, irrevocably, at a scale that still shapes every city, every supply chain, every economic geography of the nation you inhabit today. The question is simpler and harder. At what point does necessary cost become conscious sacrifice? At what point does progress require that we name what and who it consumed? The machine did not have an answer. The men who built it did. They chose deliberately and in full knowledge to keep moving forward. The ground remembers what they left behind. To understand why the machine was built, you must first understand the particular quality of desperation that gripped the United States in the decade following 1865. The Civil War had ended. 4 years of industrialized slaughter had consumed 620,000 lives, shattered the agricultural economy of an entire region, and left a nation that was technically unified but functionally fractured, a body whose bones had been reset but whose tissue had not yet healed. The physical infrastructure of the South lay in ruin. The political infrastructure of the Union lay in negotiation, and the economic infrastructure of the entire country lay in a state of violent, accelerating transformation that no existing institution was fully equipped to manage. What remained intact, what had in fact grown stronger during the war years, was the railroad industry. The conflict had demonstrated, with the brutal clarity that only military necessity can provide, that the nation which controlled the movement of men and material controlled the outcome of the war. Union generals had requisitioned locomotives the way they requisitioned cannons. Tracks had been torn up and relayed within days. Entire armies had been repositioned by rail across distances that would have taken weeks on foot. The railroad was no longer a commercial convenience. It was a strategic organ of national survival. When the war ended, that lesson did not dissolve with the peace. It transformed. The federal government, controlled by Republican industrialists who had watched the railroad win a war and were now determined to use it to win a continent, passed the Pacific Railway Acts of 1862 and 1864. These acts did not merely authorize the construction of a transcontinental railroad. They funded it, land-granted it, and structured a system of financial incentives so aggressively weighted toward speed of construction that safety, labor conditions, and engineering precision became, in the precise economic sense of the term, externalities, costs absorbed not by the companies, but by the bodies of the men doing the work. The Union Pacific would receive between 16,000 and 48,000 acres of federal land for every mile of track laid, depending on terrain. It would receive government bonds between $16,000 and $48,000 per mile, disbursed upon completion of each section. The faster you built, the more you earned. The calculation was not subtle. Into this environment arrived the labor force. They came from everywhere that desperation concentrates men. Irish immigrants, 300,000 and 400,000 of them, carrying the memory of famine in their bones, and the pragmatic fatalism of a people who had already survived the unsurvivable. Chinese workers, recruited initially in small numbers and then in waves of 10,000 and 15,000, paid less than their Irish counterparts for identical and often more dangerous work. Freed black laborers in the South, building the regional lines that connected the devastated Confederacy to the expanding national network, working under conditions that in some cases differed from the slavery that had preceded them only in the nominal presence of a wage. And behind them all, driving the pace, setting the quotas, calculating the acceptable margins of human loss against the financial incentives for speed, were the engineers, the surveyors, and the company men. By 1867, the Union Pacific was laying track at a rate that astonished observers on both sides of the Atlantic. 1 mile per day, then 2. Then, in a single legendary push across the flat alkaline expanse of Utah, 10 miles in a single working day, a record announced by telegraph to a nation hungry for evidence that it was, in fact, becoming what it believed itself to be. No one announced how many men did not survive that day. No one counted. That was in its own way the most telling fact of all. Not the cruelty of the counting, but the simple administrative decision that certain numbers were not worth keeping. The machine that would be sent into this environment was not designed in isolation. It was designed as a direct response to a specific industrial crisis. The gap between the speed the financial incentives demanded and the speed that human muscle, working alone, could physically provide. The beast was the answer to that equation. It was built to close the gap. The machine did not emerge fully formed from a single mind. It was, like most instruments of industrial consequence, the product of accumulated pressure, a convergence of existing technologies pushed beyond their original parameters by the specific and unrelenting demands of an industry that had outgrown every tool previously built to serve it. The foundational technology was the steam engine itself. By 1860, the steam engine was already 60 years into its American industrial life. It had powered textile mills in Massachusetts, riverboats on the Mississippi, and the early passenger locomotives that had first demonstrated to a skeptical public that mechanical traction was not merely possible but transformative. But the stationary steam engine and the early locomotive, for all their power, were instruments of a particular scale, a scale calibrated to existing infrastructure, existing track, existing bridges and tunnels and grade tolerances that had been engineered with the assumption that machines would remain within certain boundaries of weight and force. The railway expansion of the 1860s demolished those assumptions entirely. The grades encountered in the Appalachians, the Rockies, and the Sierra Nevada were not the gentle inclines of the eastern seaboard's established line. They were geological confrontations, walls of granite and compressed shale that rose at angles no existing locomotive could climb under load, through terrain that no existing excavation method could clear at the pace the construction schedules demanded. The hand tools of the era, the pick, the blasting charge, the horse-drawn scraper, were not inadequate in any absolute sense. They were simply too slow, too human, too calibrated to a pace of labor that the financial mathematics of the Railway Acts had rendered obsolete before the first spike was driven. It was in this context that William Sellers, a Philadelphia machinist and engineer of formidable reputation, began collaborating in 1863 with a consortium of railway investors to develop what the internal correspondence of the period referred to simply as a heavy grading engine, a locomotive scale machine capable not merely of moving along existing track, but of participating directly in the creation of new track, clearing grade, moving spoil, and operating under load conditions that would have destroyed any existing engine within days. The machine that emerged from 4 years of iterative development and 2 catastrophic prototype failures was unlike anything previously operating on American soil. Its boiler, fabricated at the Midvale Steel Works outside Philadelphia, was constructed from rolled iron plate 3/4 of an inch thick, riveted at intervals of 2 inches along seams that ran the full 11-foot height of the cylindrical shell. It carried a working pressure of 160 pounds per square inch, 40 pounds above the standard operating pressure of contemporary passenger locomotives, a margin that gave the machine its extraordinary tractive force, and that would, in later years, become the central engineering controversy of its operational history. Its weight, 312 tons in full working trim, including water, coal, and the attachment of its primary grading apparatus, was distributed across a wheel arrangement that its designers had borrowed and substantially modified from European mining locomotives. 4 driving wheels, each measuring 6 feet 2 inches in diameter, forged from cast steel at a foundry in Pittsburgh that had previously specialized in producing cannon barrels for the Union Army. The connection was not incidental. The metallurgical knowledge that had learned to contain explosive force inside a gun barrel was now being applied to containing a different kind of explosive force inside a boiler. By 1868, the first production model had been completed, tested on a private siding outside Harrisburg, and delivered under contract to the Central Pacific Railroad for deployment in the Sierra Nevada cutting operations. The engineers who watched it move for the first time recorded their observations in language that oscillated between technical precision and something approaching awe. One wrote in his field journal that the machine moved through a test grade of compacted gravel and clay the way a knife moves through rendered fat. Without resistance, without hesitation, without any apparent awareness that an obstacle had existed. The railway executives who funded it used simpler language. They called it exactly what the men in the camps would later call it independently, without coordination, as though the name were the only honest response to what they were witnessing. They called it the Beast, and they ordered 6 more. To understand how the machine killed, you must first understand how it worked, not in the abstract language of industrial progress, not in the promotional vocabulary of the railway company's circulars that described it as a marvel of American ingenuity and a testament to the productive genius of the age. In the specific mechanical, physically consequential language of what actually happened inside 312 tons of iron and steel, when a fireman opened a valve and introduced pressurized steam into a cylinder the diameter of a barrel. Begin with the boiler. The boiler was the machine's heart and its most dangerous organ simultaneously, a gap that every engineer who worked closely with the Beast understood, documented, and ultimately accepted, because the alternative to acceptance was a conversation with a railway executive about construction schedules. And that conversation had only one possible outcome. The problem originated in the boiler seam, the riveted construction of the boiler shell, that 3/4-inch rolled iron plate, joined along vertical and circumferential seams by iron rivets driven hot and allowed to cool and contract, drawing the plates together with a clamping force that was under ideal conditions, sufficient to maintain a pressure-tight joint at the specified working pressure of 160 pounds per square inch, was fundamentally dependent on the quality and consistency of the water used to generate steam. Clean water, low in dissolved minerals, produced clean steam and left boiler heating surfaces relatively free of scale. The hard mineral deposit that accumulated on the interior surfaces of the boiler shell and, most critically, on the crown sheet. The curved plate that formed the top of the firebox and separated the intense heat of combustion from the water and steam above it. The water available along the advancing construction frontier of the American West was not clean. It was alkaline, mineral-laden, drawn from sources that deposited calcium carbonate, magnesium sulfate, and silica onto every interior surface of the boiler at a rate that, under heavy operating conditions, could build a scale layer of measurable thickness within 6 weeks of service. Scale was an insulate. A scale layer of 1/16 of an inch on the crown sheet reduced heat transfer efficiency by an amount that required a compensating increase in firebox temperature to maintain operating steam pressure, which increased the thermal stress on the crown sheet itself, which accelerated the degradation of the riveted seams along the boiler shell, which reduced the actual burst pressure of the assembly below the design specification, without any change appearing on the pressure gauge that the fireman used to govern his operation of the machine. The gauge told him the pressure inside the boiler. It told him nothing about the structural integrity of the vessel containing that pressure. This was known. A report prepared in 1869 by a consulting engineer named Cornelius Ashworth, commissioned by the Central Pacific's own mechanical department, documented the scale accumulation problem with meticulous precision. Ashworth calculated that machines operating on alkali water sources without mandatory boiler washout intervals of no more than 30 days were, after 60 days of continuous service, operating at an effective safety margin of less than 40% of their design burst tolerance. He recommended mandatory washout schedules. He recommended water treatment protocols. He recommended a reduction in operating pressure for machines deployed in alkali water territories to 130 pounds per square inch. The report was filed. The construction schedule was not adjusted. The washout intervals were not enforced, not because the railway company lacked the mechanical capacity to enforce them, but because enforcing them meant stopping the machine. And stopping the machine, even for the 36 hours a proper boiler washout required, meant falling behind a construction quota that was measured in financial penalties per day of delay. Penalties that, in the calculus of the company's accounting department, exceeded the projected cost of the accidents the Ashworth report was predicting. The projected cost of accidents was a line item. It had a number assigned to it. That number was smaller than the number assigned to delay. The men who operated the beast did not choose the work the way a man chooses a profession. They chose it the way a man chooses the least dangerous option available to him, inside a set of constraints so narrow that the word choice loses most of its meaning. They chose it over starvation, over the uncertainty of seasonal agricultural labor, over the particular degradation of urban tenement poverty, over the slow diminishment of a man who has skills and no market for them, and watches his children grow thin in a room that costs more than he earns. They chose it because it paid. Not well by any standard that the men who owned the railways would have recognized as adequate compensation for the conditions involved. The standard wage for a machine operator on the heavy grading crews in 1869 was $2.20 per day, a figure that sounds, in isolation, almost reasonable, until you account for the company's stored deductions that consumed between 40 and 60 cents of every dollar earned. The tent accommodation fees deducted at source, the tool rental charges, the medical levy that provided, in return, access to a camp physician whose primary qualification in many documented cases was proximity rather than competence. What remained after deductions was rarely enough to send money home. Most men sent nothing for months at a time. The letters they wrote, the ones that survived, preserved in family collections and regional historical archives, are documents of a particular caliber of stoicism. They describe the work in practical terms, the hours, the distances moved, the nature of the terrain. They rarely describe fear, because fear, committed to paper and sent to a wife or a mother, becomes a burden transferred rather than a burden shared. And these were men who had been formed by cultures, Irish, Chinese, Black, Southern, that understood burden as a private matter. What the letters do not describe, because there was no language adequate to it that would not have caused immediate alarm, was the sound of the machine at full operating pressure in an enclosed cut, a railway cut, the trench excavated through a hillside to maintain a level grade for the track, amplified the mechanical noise of the beast into something that ceased to be sound in any ordinary sense and became instead a physical environment. The concussion of the exhaust blast through the stack, repeated at a rate of 240 times per minute at full working speed, created a pressure wave that experienced operators learned to lean into rather than resist, the way a man leans into a strong wind to maintain his balance. The screech of the valve gear, the grinding percussion of the coupling rods, the deep tonal vibration of the boiler shell itself, all of it compressed by the rock walls of the cut into a continuous assault that left men temporarily deaf at the end of a shift and, after years of exposure, permanently so. The fireman's position was the most physically demanding station on the machine. He stood on a platform measuring 4 feet by 3 feet, directly in front of the firebox door. For shifts that ran between 10 and 14 hours, depending on the construction schedule and the disposition of the foreman, he shoveled coal, approximately 1 ton per operating hour, meaning between 10 and 14 tons per shift, in a motion so repetitive and so physically specific that the muscle development on the dominant side of a veteran fireman's body was visibly asymmetrical. The shoulder and back muscles of his shoveling arm enlarged to a degree that altered his silhouette. The heat at the firebox door, measured in a rare surviving instrument log from a Central Pacific machine operating in the Sacramento Valley in the summer of 1870, reached 412 degrees Fahrenheit at platform level on hot days. When the ambient temperature was already above 95 degrees, men fainted. They were revived with water that was also used when supply was short as boiler feed water. They returned to their stations because the alternative was a wage deduction for lost operating time that they could not afford. They developed a relationship with the machine that was neither affection nor hatred, but something more complex and more honest than either. the relationship of a man to a thing that may kill him, and that he nonetheless understands better than almost anything else in his life. They knew its sounds. They knew the particular change in exhaust note that indicated a developing valve problem, the specific vibration frequency in the cab floor that meant a driving wheel bearing was running dry, the smell sulphurous sharp. Electrically charged, that preceded a crown sheet failure by approximately 4 minutes. 4 minutes if you knew what you were smelling. Less if you did not. The morning of September 14, 1872, began like every other morning on the Humboldt Cut, 4:15. The sky above the Nevada desert still holding its nighttime darkness, dense and mineral black, the stars of the high basin desert burning with the particular clarity that comes from elevation and the complete absence of any competing light. 41 men moving through the camp in the pre-dawn routine that had become, over 6 weeks of continuous operation, as automatic and as unexamined as breathing. Coffee from a common pot, bread from the previous evening, hardened overnight. The brief, wordless assembly at the machine's tender, where the day's assignments were distributed by a foreman named Patrick Connolly, a Cork man 12 years out of Ireland, who had worked railway construction from Baltimore to Sacramento, and who knew, with the diagnostic certainty of long experience, that the machine assigned to his crew that morning was not right. He had known it for 11 days. The exhaust note had changed. A subtle flattening of the characteristic sharp bark, a slight elongation of the beat that suggested incomplete steam admission, which meant either a worn slide valve or, more concerning, a pressure differential between the 2 cylinders that pointed toward uneven scale accumulation on the heating surfaces of one side of the firebox. He had reported it, twice in writing, to the section engineer responsible for mechanical maintenance on the Humboldt Division. The first report had generated a visual inspection by a maintenance crew that spent 40 minutes with the machine and pronounced it fit for service. The second report had generated a written response from the section engineer's office, informing Connolly that the machine was scheduled for a full boiler inspection at the end of the current construction phase, approximately 3 weeks hence, and that in the meantime it was to remain in continuous service to meet the section quota, 3 weeks hence. At 4:58 in the morning, the fireman, a 26-year-old Limerick man named Thomas Riordan, who had been on the railway 3 years and who had, by all surviving accounts, an exceptional instinct for the machine, detected the smell, sulphurous, sharp, electrically charged. He had 4 minutes, by the experiential knowledge of men who had survived similar events on other machines on other lines. He used the first minute to close the throttle and apply the independent brake, reducing speed from the working pace of 4 miles per hour to approximately 2. He used the second minute to shout, in a voice that several surviving witnesses described as remarkably controlled given the circumstances, for the men working the grading attachment at the front of the machine to clear the right-of-way immediately. Some of them heard him. 11 of them did not or could not, over the noise of the cut. The crown sheet failed at 5 minutes and 3 seconds after Riordan detected the smell, 63 seconds beyond the experiential margin. The failure was not the gradual hissing decompression of a weeping seam. It was catastrophic and instantaneous, a structural collapse of the thinned, scale-insulated, thermally degraded plate that released the full pressure of the boiler, at that moment reading 172 pounds per square inch, 12 pounds above the specified working pressure, into the firebox and cab in a single violent event that the surviving engineering analysis would later describe, in the effectless language of technical assessment, as a rapid, uncontrolled release of stored thermal energy. The boiler did not explode in the cinematic sense. It did not fragment into shrapnel and fire in the manner of popular illustration. It vented catastrophically, directionally, with a force that the subsequent investigation calculated at the equivalent of 4,700 pounds of pressure applied instantaneously to every surface of the cab interior. Thomas Riordan was killed immediately. Patrick Connolly, standing 12 feet from the cab on the ground level, was thrown 31 feet by the pressure wave and survived with 3 broken ribs, a ruptured eardrum, and burns covering 40% of his left arm and shoulder. Of the 11 men who had not cleared the right-of-way, 7 were injured by flying debris and scalding water vapor. 4 were killed, 6 dead in 4 minutes and 63 seconds. The machine itself, the boiler shell intact, the driving wheels unmoved, the 312 tons of iron and steel absorbing the catastrophic failure of a single internal component with the indifferent structural resilience of something built to survive almost anything, sat in the Humboldt Cut, venting the last of its pressure into the desert morning air, and waited. 3 days later, a maintenance crew arrived, replaced the crown sheet, conducted a boiler washout that should have been conducted 31 days earlier, recalibrated the pressure gauge, and returned the machine to service. The construction schedule had fallen behind by 72 hours. That figure was recorded in the section engineer's weekly report to the divisional superintendent. The names of the dead were not. The Humboldt Cut disaster was not an anomaly. It was a data point in a pattern so consistent, so thoroughly distributed across the geographical and chronological span of American railway construction, that the word accident, with its implication of randomness, of the unforeseeable convergence of independent variables that could not have been predicted or prevented, becomes in honest application indefensible. Between 1865 and 1890, the United States Bureau of Labor Statistics, in its intermittent and chronically underfunded attempts to quantify the human cost of industrial expansion, recorded 4,387 railway construction fatalities, attributable directly to machinery failure. The Bureau's own internal correspondents acknowledged that this figure represented at best 60% of actual deaths, the remainder lost to the administrative indifference of companies that were under no legal obligation to report worker fatalities to any government body, and that exercised that freedom of omission with the systematic thoroughness of organizations that understood, precisely and in financial terms, what accurate record-keeping would cost them. The true number, by the Bureau's own corrected estimate, was somewhere above 7,000. 7,000 men killed by machines that their operators had documented as dangerous, that consulting engineers had formally identified as operating beyond safe parameters, that the companies that owned them had calculated, in writing, in ledgers that still exist in railway archive collections from Sacramento to Washington, as an acceptable source of loss against the financial returns of uninterrupted construction. The legal framework that surrounded these deaths was, by any contemporary standard of industrial accountability, essentially non-existent. There was no federal workplace safety legislation. The concept of employer liability for worker injury was governed by the fellow servant doctrine, a legal principle established in English common law and enthusiastically adopted by American courts, that held an employer immune from liability for injuries caused to one employee by the negligence of another. In practical application, this meant that a fireman killed by a crown sheet failure on a machine that had been documented as dangerously scaled could not generate a successful claim against the railway company because the failure could be attributed, and was routinely, in the boilerplate legal responses of railway company attorneys, to the negligence of the maintenance crew who were fellow servants, rather than to the policy decisions of the company's mechanical department. The doctrine was not a loophole, it was the architecture. It was the legal structure specifically suited to an industrial economy that required large concentrations of labor operating dangerous machinery, and that needed, with the same urgency that it needed coal and iron and right-of-way land grants, protection from the financial consequences of the deaths those conditions produced. Into this architecture walked the labor organizers. The Brotherhood of Locomotive Engineers, founded in 1863, had by 1872 established a presence on most of the major railway lines of the Northeast and Midwest. Its initial demands were modest by any standard that does not begin from the assumption that a worker's life is worth less than a construction schedule. Standardized shift lengths, mandatory maintenance intervals, the right to refuse operation of a machine formally documented as unsafe without loss of wages or position. The railway companies rejected every demand with a uniformity that suggested coordination. In some cases, the coordination was documented. In the internal correspondence of the Central Pacific's Labor Relations Office, a circular distributed to divisional superintendents in the spring of 1873 instructed them to terminate, without severance, any employee found to be associated with Brotherhood organizing activities, and to replace terminated workers from the available pool of recent immigrant labor, men who had not yet learned enough about American industrial conditions to understand what they were being asked to accept. A circular used the word replace with no surrounding language of regret or qualification. It was a logistics term, a supply chain term. The men were inventory. The last of the original Beast-class heavy grading locomotives was retired from active service in 1893. Not because it had become dangerous, though it had progressively and documentably. Over 25 years of deployment across terrain that ranged from the granite walls of the Sierra Nevada to the black clay floodplains of the Mississippi Delta. It was retired because it had become obsolete. The second generation of heavy grading machines, built to refined specifications that incorporated, without acknowledgement, without attribution, without any formal institutional recognition of the engineering knowledge that had produced them, most of the recommendations contained in the Ashworth Report of 1869 were simply more efficient. They moved more earth per operating hour. They consumed less coal per ton of spoil displaced. They failed less catastrophically because their boiler seams were constructed to tighter tolerances, and their pressure relief systems were designed with a redundancy that the original machines had lacked. They were safer, measurably, engineeringly, demonstrably safer. 24 years after a consulting engineer had documented exactly how to make them safer, the machine was moved to a storage siding outside Reno, Nevada, where it sat for 11 years, slowly oxidizing in the high desert air. Its boiler cold, its driving wheels motionless on rails that had been laid in part by the labor of men it had killed. In 1904, it was scrapped. The iron and steel of its construction were melted down and recast into components for the next generation of infrastructure. Water pipes, bridge supports, the structural members of buildings in cities that were growing with an energy that still had not paused long enough to look backward at what had been consumed to make them possible. Nothing of the machine survives in physical form. What survives is the record, incomplete, unevenly preserved, distributed across archive collections that were never designed to be read together as a single narrative. The Bureau of Labor Statistics ledgers, the Central Pacific Mechanical Department reports, the Brotherhood of Locomotive Engineers organizing correspondence, the field journals of surveyors and engineers, the letters of workers that found their way into family collections, and from there, occasionally, into the holdings of regional historical societies. Taken individually, each of these documents tells a partial story. A technical story, or a labor story, or a financial story. Taken together, they tell the story of a civilization in the act of making a decision. Not once, not in a single dramatic moment of moral failure, but continuously, incrementally, in 10,000 small administrative acts of calculation and omission, about whose lives were worth counting and whose were worth spending. The railroad was completed. That fact is not in dispute and should not be minimized. The transcontinental line, driven to its ceremonial completion at Promontory Summit, Utah, on May 10, 1869, with the driving of a golden spike that was connected by telegraph wire to a signal system that transmitted the impact simultaneously to both coasts, was a genuine achievement of the first order. It compressed a 6-month overland journey into 6 days. It integrated a continental economy. It made possible forms of agricultural, industrial, and cultural exchange that transformed every aspect of American life within a generation. The cities it connected grew, the regions it opened developed, the nation it bound together became, in the decades that followed, the dominant industrial economy on Earth. These things are true. Also true, the men whose bodies made it possible were, with systematic thoroughness, excluded from the prosperity it generated. The Irish laborers who had spiked rails across the Great Plains returned, most of them, to the urban poverty of the eastern seaboard. their wages consumed by the company store, accounting that had been specifically designed to ensure that a man could work himself to the edge of death for 2 years and emerge with less than he had started with. The Chinese workers who had carved the machine's path through the Sierra Nevada, blasting tunnels through solid granite, lowering themselves in wicker baskets down vertical cliff faces to place explosive charges, doing the work that the railway's own superintendent, Charles Crocker, acknowledged no other available labor force would attempt, were excluded from the Promontory Summit ceremony entirely, and excluded 4 years later from the United States itself by the Chinese Exclusion Act of 1882, which cited, among its justifications for the legal elimination of an entire population from American civic life, the threat that Chinese labor posed to the wages and conditions of white workers. The men who had built the railroad were deported from the country the railroad had built. The machine that had worked alongside them was melted down and recast, and the nation that had been constructed on the combined labor of both moved forward into its industrial century with the same quality of motion that had always defined it. Kinetic, consuming, not yet ready to stop and look at the ground it was leaving behind. There is a photograph taken in 1870 by an unknown photographer working somewhere along the Nevada line that shows a heavy grading locomotive, possibly one of the original Beast-class machines, possibly not. The resolution does not permit certainty. Sitting at rest in a desert cut between 2 walls of exposed rock, the machine fills the frame almost entirely. Its dimensions overwhelm the landscape around. In the lower left corner of the image, at the edge of the frame, almost cropped out of the picture entirely, stands a single man. His face is not visible. He is looking at the machine. He is very small. That proportion, the man and the machine, the body and the system built around it, the individual life and the institutional force that consumed it, is not a metaphor. It is a measurement, a precise, photographic, historically documented measurement of exactly how the 19th century understood the relationship between human beings and the instruments of progress they were asked to serve. We built the machine, we laid the track. We are still, in ways that have changed their form but not their fundamental geometry, living inside the calculation that decided some lives were worth less than the schedule they were asked to keep. The ground remembers. The question is whether we are willing to.